In this video, we're going to talk about an operation on vectors called the dot product. But instead of just telling you what the dot product is, I want to begin with a geometric problem. So consider this setup. I have two vectors, a vector u and a vector v, and they have an angle between the two vectors. Well, the question is, how can I find what the angle is between these two vectors? This is a very natural problem. Now, whenever I have two vectors joined in this way, they actually form a triangle if I consider the third side to be the vector u minus v. And now that I have it as a triangle, I can use rules from geometry. In particular, I can use the cosine law. So the cosine law applies to triangles, and it says the following. If I look at what the length of this u minus v vector is, and I look at the square of that length, then this is nothing but the square of the u vector's length and the square of the v vector's length minus twice the length of u, that's the one side, the length of v, that's the other, cosine of theta. So this is the cosine law applied to our particular triangle, where I'm using the notation of vectors and the length of a vector just to refer to the length of a side of a particular triangle. All right, well, let's expand this formula a little bit. So first of all, let me look at the length of u squared. Well, if u is a vector that has components u1, u2, and u3 in 3 dimensions, then the length of the vector u squared is just the u1 squared plus the u2 squared plus the u3 squared. Likewise for the v vector, the length of v squared is just v1 squared plus v2 squared plus v3 squared. All right, making progress. Now let's look at the length of u minus v squared. Well, if I expand out what the length of u minus v squared is, the first component of the vector u minus v is u1 minus v1. The second component is u2 minus v2, and the third component is u3 minus v3. So then if I apply my formula for length, this is going to be equal to the u1 minus v1 squared plus the u2 minus v2 squared plus the u3 minus v3 squared. I'm going to step out of the shot a little bit because there's not enough space, and I'm going to get rid of my triangle. But if I then expand that, what I'm going to have is, well, expanding the u1 minus the v1 squared gives me u1 squared minus 2u1 v1 plus v1 squared, and so on, expanding out. Now, what I want to note is, if I look all the way at that top line of the cosine law, is that many of the things that I've got now where I'm expanding the left-hand side appear on, in fact, the right-hand side of our cosine law as well. Indeed, if I focus on the u1 squared and the u2 squared and the u3 squared that's in my expansion, that's nothing but the length of u squared. Likewise, if I focus on the v1 squared, the v2 squared, and the v3 squared in my expansion, that's nothing but the length of v squared. So if I look at my equality, I have a lot of common terms on both sides, so I'm going to cancel everything. And what that leaves is that on the left-hand side, I'm going to have minus 2 u1 v1 minus 2 u2 v2 and minus 2 u3 v3. And on the right-hand side, I have that minus 2, the length of u, the length of v, cos theta. That's all that remains. Cancel out the minus 2's, and you can go and solve for theta now and say theta is arc cosine of some messy numerator divided by the length of u times the length of v. In fact, this formula is going to be our answer for the angle between two vectors. So let's just state that. The angle between two non-zero vectors can be given by this expression theta is arc cosine of some numerator divided by the length of u, the length of v. Now, the thing in the numerator is a bit messy to write out, and more importantly, the thing in the numerator shows up, as we're going to see in the future, over and over and over again. So the thing in the numerator is important enough that we may as well give it its own name. We're going to call it the dot product. So here it is, our definition of the dot product for two vectors u and v. Their dot product is the product of the first components plus the product of the second components plus the product of the third components. Indeed, you could do this in a higher number of dimensions. If you had fourth and fifth and sixth components, the dot product would generalize there as well. Now that we have this dot product, we can go and fix our angle theta. We can clean it up a little bit, and we can say just arc cosine of the dot product of u and v divided by the length of u, the length of v. One thing to note is that this is sort of a multiplication of two vectors, but it works in a somewhat strange way. If you think about what u and v are both vectors. So u dot v, what it is a product in some sense of two different vectors. But what's the output when you go and smash them together in this way? Well, u1 v1 plus u2 v2 plus u3 v3, all of those are scalars. They're multiplications and additions of scalars. So the right-hand side isn't just a scalar. So what does the dot product do is it takes two vectors, two three-dimensional vectors in this case, and gives you out a real number. It gives you out a scalar. Let's do one more example. Let's do a special case where the angle theta is known to be pi over 2, 90 degrees. Well, in this case, if I plug it into my formula, so theta is pi over 2, and we're saying that this is arc cosine of the dot product divided by the length of u times the length of v. If I then take that expression and I take cosine to both sides, I'll get cosine of pi over 2. And then cosine of arc cosine of the argument is just going to be the argument again. So cosine of pi over 2 is just the dot product divided by the length of u times the length of v equal to 0. And what does that imply? Well, that implies that the dot product is going to be 0. So this motivates a new definition. I'm going to say that when the dot product is 0, I will call the two vectors orthogonal, which means we think that they have an angle of pi over 2 between them. And that is our new definition of orthogonal. But noting that our definition of orthogonal here is allowing our vectors to be 0 as well, whereas when we were talking about angle previously, we were insisting they were non-zero, so a slight discrepancy there on that fringe case. But nevertheless, we have this definition of an orthogonal vector.